Okay. Um, yeah, so thanks everyone for joining today. It's my pleasure to introduce Hima Lakkaraju, who's an assistant professor at Harvard University focusing on explainability, fairness, and robustness of machine learning models. And she's been doing a lot of great work in all of these areas. And yeah, today she'll be talking about some of her work on reliable and robust model explanations. So yeah, whenever you're ready.
Thank you so much, Oscar. Thanks for having me at this seminar, and thanks so much, everyone, for your time. Hopefully, everyone can see my slides and I can get started. I guess that's yes, probably. Yeah. Okay. All right. So today I'm going to talk about some of our recent work on thinking about reliable and robust model explanations, and I'll go through all the details about what I mean by each of these. But I just wanted to mention that I'll also pause periodically for questions during the talk, and we can take questions at that point, and also happy to answer any other questions at the end of the talk as well. Okay, so with that, I'll jump into today's talk. So we all have encountered, or at least like heard about or seen scenarios like this, where, for example, in healthcare, a doctor is making recommendations of treatment for a patient and doing disease diagnosis and so on. And in settings like criminal justice, judges are making decisions about bails and, of course, other critical decisions, right? So in several of these settings, there has been a lot of talk or interest in thinking about how machine learning models can be employed in these settings to help these decision makers, right? So in some settings, especially in healthcare, there has probably been like more rapid progress, and people are like building all kinds of tools that can assist doctors. Some are even being like tested for deployment and so on. So ML is being thought of as like this holy grail that will improve decision making in several of these domains like healthcare and policy and things like that. So, a lot of prior research has already argued that interpretability will become key in such settings. And the reason is that we don't see machine learning models as replacements to human decision making in these settings. We rather see it as a complement or as an assisting tool to human decision makers. For example, if we think of the healthcare scenario, there will be a doctor still making treatment recommendations, disease diagnosis, but they'll also have a tool at their disposal that can potentially tell them the probability of a diagnosis and help them consider different treatment options and the costs associated with them or the risks associated with them and so on, right? So in such scenarios, as opposed to just providing a decision maker with a prediction, whether it's a label, a yes or a no, or a particular diagnosis or a probability, it would also be useful to provide more details about the rationale behind the algorithm's predictions. What kinds of features is the algorithm emphasizing on, or like what is its logic that it's employing in making this prediction or this decision? All that information can be extremely helpful in telling a doctor or any other decision maker how much and when to rely on algorithmic predictions, right? So interpretability can be a key in these settings. So when we think about interpretability in ML, so what is the situation so far, right? So there are several simpler classes of models. For example, linear models, shallow decision trees, simple rule-based models with like fewer number of rules, and so on. A lot of prior work has talked about how these models are easier to understand and they can help people or any end users like quickly realize what is going on in the model, right? So that is, of course, one way to think about how to understand the rationale behind algorithms predictions. So these models make it a lot more easier. But recent research has also shown that complex models achieve comparatively higher performance. For example, deep nets, random forests, and so on. So several domains, particularly involving high dimensional data, like whether it's images or whether it is graphs, neural networks or deep neural networks more specifically have been consistently beating other benchmarks in terms of performance, right? So given that this is the world that we are living in, where complex models are achieving better accuracy, but simpler models are often touted as more interpretable, what is the solution, right? So how do we think about achieving interpretability? And the solution that has become popular over the past few years is the following, which is build a model as complex as you can just to optimize for accuracy, right? So you can make your model as complex as you can as long as you're happy with accuracy. That's good. And then in a post hoc fashion, explain these complex models using simpler models. So there has been a huge surge of approaches proposed under this broad literature, which is termed as post hoc explanation techniques, right? So build any of your favorite models, that whatever you like, with the best possible accuracy numbers, and then take that model and explain it in a post hoc fashion. So that is what a lot of explainability or explainable AI literature is revolving around. Okay. So the agenda for today will be the following. So I'll first talk a little bit about some post hoc explanation techniques, some popular post hoc explanation techniques. I'll introduce them and I'll also talk about the challenges associated with them. Then I'll present a couple of our recent research. So one is on explanation with guarantees, which is how to build more reliable versions of popular explanation algorithms such as LIME and SHAP. And then, hoping that time permits, I'll also talk about some work where we tried to construct explanations that are robust to distribution shifts. And this, of course, joint work with Ospert. And then I'll present a summary and conclusions. Okay. All right. So I'll start with post hoc explanation techniques. Let's jump right into this. So, post hoc explanation techniques typically regard a given complex model as a black box, so they require little to no internal details of the model. So, typically, the maximum that these techniques would require is gradient access. In some cases, or actually in several cases, you don't even need that, you just need query access, right? So that's why I'm calling it like a minimal access. So when you want to employ a post hoc explanation technique, all you need is being able to throw in a data point at the model and then getting a prediction out of the model. Or in the worst case, these techniques are requiring like gradients, right? So these post hoc explanation techniques. And there are several types of post hoc explanation techniques, and these may differ based on what behavior of the model they're explaining or the precise techniques being used to explain model behavior. For example, local versus global approximations. So, local being we are trying to explain the rationale behind an individual prediction, global approximation or global post hoc explanation techniques try to explain the complete behavior of a given model in its entirety. And gradient based versus perturbation based is another popular characterization of these techniques. Gradient based techniques, as the name suggests, leverage gradients or utilize gradients to explain the behavior of a complex model. And perturbation based techniques are things that actually use perturbations of data points to understand how a model is behaving, right? And just to name drop a few things, some of the popular post hoc explanation techniques include LIME, SHAP, Anchor, Muse, gradient times input, integrated gradients, and so on. Okay. So in this first part of the talk, I'll be focusing more on local explanations and more specifically on two methods, LIME and kernel SHAP. I'll talk quite a bit about LIME, and most of the insights that I'll be discussing as we think about LIME are also applicable to kernel SHAP, right? So that's the context for the first piece. All right. Local explanations. As I just said in the previous slide, the goal here is to explain the rationale behind individual predictions of a given black box model, right? So why do we need this? This can help us vet if individual predictions are being made for the right reasons, right? So if the right features are being used, and if the prediction is kind of not relying on spurious features, it helps us make all these checks. And this can also help us unearth or shed light on any biases that may be occurring in model behavior in the local neighborhood. Right? So that's where local explanations can be helpful. LIME and SHAP are two very popular local post hoc explanation methods, and both of these are model agnostic. They actually require no access except query access to the model. They don't need to know any internal details of the model, not even gradients. All they require is we should be able to input a data point to the model and get a prediction. That's all they require. That's the level of access they require. Okay, these are going to generate local explanations, which means they'll give you an explanation for any given individual prediction of a classifier, and we'll talk a little bit about how they do that very soon. And the outputs of these methods is that they output feature importances or feature attributions for individual instances. These feature importances capture the effect of each feature on the black box prediction, right? So that's roughly how we can think about their output and what these methods do. So, what is the intuition or the rationale that these kinds of local post hoc explanation methods are exploiting? Right, the intuition is actually very simple. It's the following. So, if we look at this particular picture, you see some light blue shaded region and then a light pink shaded region. You can think of that as the decision surface of a complex nonlinear model like a deep neural network. So, the intuition here is that while complex models have highly nonlinear decision surfaces and are often harder to understand from a global point of view, if we zoom in enough to a local pocket, we can see that these models behave in a linear fashion. Right. So, for example, if we zoom in around this particular point, this red plus mark point, we can see that even this complex nonlinear model is roughly behaving like a linear model, and hence we can approximate its behavior using a linear model, right? So that's the intuition that these kinds of methods like lime and shab exploit. So from here on, I'll be focusing more on lime just to kind of get the intuitions right, but all these insights apply for kernel chap as well, and more generally shab as well. So how does lime work? Like, what is basically the procedure? How do we get a linear model explanation, or what is the explanation that lime produces, and how do we get it? Right. So the procedure is actually pretty simple. So let's say we need to explain the prediction of an underlying complex model for this particular data point that I'm highlighting on the screen now. So how does lime do it? So it takes that point, it adds some noise and kind of perturbs that point slightly and creates a bunch of points around that main instance of interest, right? So now we have an entire neighborhood of points. So now what Lime proposes is now on this local neighborhood, fit a linear model which essentially mimics the predictions of the underlying complex model, right? So that's all. That's a very simple idea. The idea, again, just to kind of reiterate, that is, take that point that you care about, whose prediction you want to explain, perturb it a bunch of times slightly, and then generate a whole bunch of points around that point, fit a linear model which basically mimics the predictions of the underlying complex model. And this linear model will now give you an interpretable version of the complex model in the local neighborhood, so you'll get feature importances from that linear model, right? So that's the intuition. And perturbations are done in different kinds of ways. Lime paper also suggests a couple of ways of perturbing. There are also other perturbations proposed by other papers. One approach is pretty simple, which is add some small Gaussian random noise. The other approach is basically the following, which is, you can binarize all your features, make everything 0 and 1, and then out of all the features which are set to a value of 1, randomly pick a subset of those features and flip their values to 0. So yeah, perturbations are done in different ways, but the high level idea is something that we just discussed. Okay. All right. So what do Lime explanations look like, right? So this is Lime explanation for a tabular data, the upper portion of it. What you see here is actually point-wise estimates of feature importances. So for example, there is a feature in this data called misdemeanor charge, and you see that the feature importance for that is 0.225, and green basically means a positive feature importance and red means a negative feature importance, right? So for each of these features, we basically have a value for feature importance, either positive or negative. And in the case of images, you can think of this as this will output the important features. For example, for this particular image, the top three important features are, this super pixel or this image patch, this other piece, and also the face of the dog here and the electric guitar, as you can see, right? So this is typically the kinds of explanations that Lime outputs, basically feature importance associated with each features, which we can use to get the top K features that are contributing to model prediction in this particular local neighborhood. So here is how the formulation for Lime looks like. So essentially it has two terms and we are trying to minimize additive combination of these two terms. So the first one is a loss function and I'll get to that in a bit. And then the second one is the complexity function. So given that we are fitting a linear model here, this complexity function can be thought of as just number of non-zero weights in the linear model explanation, right? And we just want to minimize those. And what is this loss function? This loss function is basically trying to ensure that the predictions of this linear model that we are fitting and the predictions of the underlying complex model are the same, right? So it's trying to minimize. So F is this underlying complex model and G is this explanation or the linear model that we are trying to fit in, right? So we are trying to minimize the gap between the predictions of these points across all Z, where this big Z is basically the local neighborhood. And we are doing so by accounting for some kind of a weighted combination of these terms. And the weights are coming from some function pi x of Z. So which is actually a distance function. It could be like a cosine or an L2 distance function. Why are we using this distance function? The reason or the intuition here is that we want to put more weightage on points that are closer to the original instance than those that are farther away, right? So because the points that are closer to the original instance are more likely to be in the actual local neighborhood than points that are farther away. So this also helps us even out any effects of the perturbation procedures, because some perturbation procedures may generate like points that are much farther off. We really want to dampen down their effect when we try to fit this linear model, and that's what this distance function helps us do. Okay. All right. So far everything sounds good. So we are able to fit like a simple sparse linear model there and try to understand what's going on with a complex model underneath. So where does the problem lie, right? So there are several challenges with methods like Lime and SHAP, and the first one being, how do we even ensure that these explanations are faithfully capturing the behavior of underlying models, right? So if somebody gives me an explanation and says this is a Lime explanation, how do I test it? Like, what is my litmus test? What is my sanity check that helps me understand how good is this explanation? And there are several methods proposed for it. I'm going to touch upon one very popular one and highlight what are the challenges with it, right? So a popular metric that has been used is something like this, which is compute a weighted accuracy or a weighted R square on the perturbations that Lime itself is generating, right? So Lime's procedure is generating a bunch of perturbations or points in the local neighborhood. So now the thing is, take those points, now see the predictions of the local linear model, which is our explanation produced by Lime, and then the underlying complex model, and see how well they match, right? It's almost some kind of a weighted accuracy. Instead of computing this with respect to some ground truth, you are computing with this with respect to the predictions of the underlying black box, right? So weighted accuracy or weighted R square. Now, there have also been several works that criticize this metric because this is making the evaluation dependent on the perturbations generated by Lime itself, right? So, how do we know that the way we are thinking about the perturbations or the way Lime is generating the perturbations in the local neighborhood? How do we even know that that is the right local neighborhood? So, people have raised a lot of criticisms and critiques about this, that there's not a reliable measure. And given this, like, we can't really say if this is the perfect measure to tell us if a explanation is faithfully capturing the behavior of the underlying model, right? So there are also several other measures, and each of them has their cons, and there have always been challenges with respect to coming up with like a good reliable measure here. So the bottom line is, there is not a very easy and straightforward way to tell how faithful a given explanation is, right? So there are more challenges. So the other thing is this metric called as local Lipschitz constant, which was proposed by David Alvarez Mellis. This is trying to capture the stability of an explanation. And what do I mean by stability? Stability means, let's say if we take a data point and if we perturb it slightly, add some small noise to it, the hypothesis is that the explanation of this perturbed point should not change drastically from the original point, right? So assuming, again, this is making the assumption that the behavior of the underlying model is also not changing. right? So that is stability. So in order to capture this, this paper by David Alvarez Millis came up with this local Lipschitz constant, which is basically measuring how much is your explanation changing when you make a small change to your data instance itself, right? And the smaller the change in the explanation, the better the quality of the explanation method. So that's how they're thinking about it. And what they showed in their results is that these approaches like LIME and SHAP, which rely on perturbations, they are unstable. They are much more unstable compared to some of the other approaches out there with smooth out gradients and so on. So there is a problem with stability of these approaches. Some of our recent work actually showed this more prominently, that it's not just stability, there is a whole other bigger problem, which is that of consistency. What do I mean by that? If I just repeatedly run LIME on the same data point with actually the same parameter settings, we see that it gives you different explanations. And that makes it even worse, because now I just don't know which explanation is the right one, right? So here I'm showing you like 4 pictures. These 2 are the case where the underlying model is a linear model, and these 2 are the cases where the underlying model is a non-linear model. And these blue, so each, the blue region that you see, it is actually comprised of several blue lines, and each blue line is an explanation. So you can see there are like several different kinds of explanations being produced, like throughout, like no matter the model is linear or non-linear, right? So this effect is more pronounced, of course, here, where the underlying model is linear, and then the number of perturbations that you are using is fewer, right? So whenever you have fewer perturbations, you're basically running into this problem that LIME is just generating different explanations each time you rerun it.
Can I ask a
Deepak, you
quick
had a
question?
question? Yeah.
Hi, Hima. Nice to
Hey.
see you. Uh, is this, when you say consistency, in what way do you mean it? Because, you know, is this like is it asymptotically consistent or not? Or like, for example, in the limit, will it converge to a single answer? Or is it like, in what sense are you using the word consistency?
Yeah, when I use the word consistency here, I am saying that so LIME is generally giving you a vector of feature importances, right? So that's its output. Now, when I repeatedly run this method, I get different vectors each time. So that's a lack of consistency that we are talking about. Is that clear? So basically the feature importances are not the same. If I just take the same algorithm, set the same parameter values, just rerun the algorithm, I get a different answer in terms of feature importance values.
But that's a function of the number of perturbations, right?
Yeah, so that's, I'm just getting to that. Yes. So because there is, I think the deeper problem is that there is no good way to say here is a good enough number of perturbations, right? So that's the key problem, and I'm just getting to that. Yeah. So yeah, so that's the thing. So what you see here is that, you know, when you have fewer perturbations, you are probably seeing these regions are much wider, and when you have more perturbations, these regions are kind of like narrower or like much smaller, right? So what you can infer is like maybe the problem will go away if you just keep increasing the number of perturbations, right? Uh, yes, that's a fair point, but nobody knows what is the optimal number of perturbations. And then the answer is, can we just use a very, very large number like 20,000, 1 million? Can we just like put a ridiculously high number? That is also challenging, because then it makes the scalability a big issue, right? Because querying complex models like these complex neural nets like ResNet or AlexNet and so on repeatedly for labels can be computationally prohibitive. If you're saying I'm going to generate 1 million perturbations for each point, and my data has 10,000 points, and I have to generate LIME explanations for all of those, this can get like ridiculously hard to do, right? So just kind of increasing the number of perturbations to a very big number and just running it is not really a very feasible option, especially when you're running it on large data sets, right? So that's the problem. So there is a scalability challenge associated with getting to reliable explanations, right? Okay, so given that I've highlighted a bunch of problems here, now what do we do about all of these? Okay, So I'll talk about one of our recent researches, which is reliable post hoc explanations, which tries to model uncertainty in explanations. This joint work with students Dylan Slack and Sophie Hilgard and Samir Singh, who's an associate professor at UC Irvine. Okay, so what is our approach here, right? So this is the Lime explanation that we talked about just earlier. So it was giving us point-wise estimates of feature importances, right? And in fact, what we had a problem with was that if I run Lime with 100 perturbations, maybe I'll get different feature importances. If I run it with 2000 perturbations, I'm getting different feature importances. I just have like no way of really consolidating these. Now, what do? Is instead of thinking about these as point-wise estimates of feature importances, how about we define these as distributions, right? So this is the Bayesian version of Lyman Sharp that we are proposing in this work. And this essentially, as opposed to defining point-wise feature importances, this almost kind of defines a distribution, okay? So now when you run it with 100 perturbations, what you see is that this zone or the region of uncertainty is much more higher. Whereas if you run it with 2000 perturbations, you are much more certain and your region of uncertainty has narrowed down, right? But it has not kind of gone all over the place. You can still consolidate the two views. You can see that the 100 perturbations, you get more uncertain explanations. With 2000, it's less uncertain, but everything is within this kind of a region, right? So now you can start thinking about how certain an explanation is, or how confident we are about an explanation. Okay. All right. So what do we do here? So the first step that we do here is actually pretty reasonably simple. We try to construct a Bayesian locally weighted regression model, which can accommodate Lime and Sharp weighting functions, right? So I'll talk again about Lime just for the sake of simplicity, but we did a similar thing for Sharp, right? So what we did here is Y is basically the black box prediction of a given point Z. So Z you can think of as a perturbed point, like a perturbation, right? And Y is basically sampled from this kind of a distribution where we have a phi transpose, which is phi is a vector of feature importances that we will estimate. And then Z is essentially this perturbed data point that we can get by perturbing the original X point, right? And plus some epsilon, where epsilon itself is modeled as this term, like a Gaussian with a zero mean and some variance. So the sigma square here is a parameter that we will set using some prior here. But the important thing to note is this pi x of Z. So this is the same weighting function that we saw in the Lime formulation a few slides earlier, right? So what this tries to do, same function, same functionality. This is essentially trying to ensure that the points that are farther away from the original instance X, they can have a higher variance, right, in their prediction. But the points that are closer to X, they will have a smaller variance, so that the prediction is more closely aligned with this feature importance vector, right? So that's its purpose. And what you see at the bottom of the screen are the priors on phi, which is the feature importance vector, and the prior on the sigma square, which is the numerator of the variance for the epsilon, which is the noise function, right? So that's a simple trick. But from here, we go further, and then of course due to conjugacy we get these posteriors which are scaled inverse chi-square and normal. So we also kind of resolve, or like basically resort to using the previous form that we propose here. Because it has one nice property, it allows us to compute these parameters that we care about as closed form, right, or in closed form. And if you see the mean estimates of these parameters, for example, the mean estimate of phi transpose, which is the feature importance vector, that still coincides with the Lime and Sharp, the way we have defined our previous formulation. So you still have the mean estimates that coincide with those, but now you have this whole uncertainty distribution on top of just the mean point-wise estimates. And this kind of a Bayesian version of this model captures two kinds of uncertainty. One is the feature importance uncertainty, which is basically the uncertainty associated with the vector phi we have been using. And how do you compute that? we can compute the posterior mean using this equation, right? So this is a closed form equation. And once we do that, we can obtain the credible interval around it by repeatedly sampling from the posterior distribution, which is basically this one, right? So we can just estimate the mean and then we can sample from phi in order to determine this region of uncertainty. And we also have this error uncertainty, which essentially captures how well our explanation models local decision surface of the underlying black box, and that again can be sampled from this distribution that you can see on the screen. Okay. So the interesting piece in terms of functionality about this work that was harder to get earlier was users can now provide inputs. For example, a user can say that I want my feature importance interval to lie within, say, plus or minus zero point 0.5 of the mean that you're giving me, with 95% confidence. So that is the kind of explanation that I need. Now you go and figure out how many perturbations you need to use. You go and figure out all the details and get me an explanation that satisfies these constraints, right? And we can do that. We also have some theorems here, some theoretical results, which can allow us to estimate the required number of perturbations for a given user specified level of uncertainty, right? So users can now provide us with inputs like, here is the width of my interval, my importance should lie within that with 95% confidence. Now it's up to you, go use your method and we'll estimate the required number of perturbations and everything and come up with this explanation that satisfies that user specified constraint. We also do one more thing, which is instead of sampling perturbations randomly and querying the black box, we try to improve the efficiency of the sampling procedure. And as part of that, we choose points that the learning algorithm, that the baseline learning algorithm is most uncertain about, and only query the black box for their labels. So this also helps us to get to the explanation in a much faster way, right? So all these pieces put together allow us to construct explanations with which satisfy user defined levels of confidence in an efficient manner. Okay, so I'll talk about some results now and then happy to answer more questions. So one of the first results that we have is thinking about the calibration and the quality of our uncertainty estimates. And we compute what fraction of true feature importances fall within our 95% credible intervals that we come up with, right? So how do we compute the true feature importances? Again, this is not practical, but just for the sake of this experiment, we tried it. It took a very long time for us. But basically, true feature importances are computed by running Lyman SHAP for an extremely large number of perturbations. In this case, that number turns out to be like 20K. We actually tried for 100K and 500K, but the values were like the same as what we could get at 20K. So it was like that was the sweet spot. And those were the true feature importances. And we do this experiment with different data sets, image data sets, tabular data sets, and so on. So these are the values that we get. And the closer these values are to 95, the better, because that means the true feature importances are falling within our intervals that we output 95% of the time, right? So that is the calibration that we are thinking about. And if you look here, Bayes Lime, it's like pretty well calibrated. Bayes SHAP, not so much. There are some technical reasons for it, but like it's also not super bad. It's like roughly within a reasonable interval, like within like 5 absolute points, for example, right? And the other experiment that we did is to evaluate the correctness of the number of perturbations. So how do we know that the number of perturbations that we are estimating empirically, how do we know that that is correct? So for this, we basically set a desired interval width and 95% confidence interval. And then we plot the observed width versus the desired width, right? So we'll say this is the desired width and we want this width of the feature importance interval at 95% confidence. Now we'll see what happens to the observed width. And this plot, essentially being a linear piece here, at least the mean values, tells us that the observed width and the desired width are like coinciding, which basically shows that our estimates of perturbations are probably on the right track. Okay, so this is a evaluation of the stability. In some of my previous slides, I talked a little bit about this metric called local Lipschitz constant, which is trying to estimate how big is the change in explanations given a small change in the data instance, right? So given a small, kind of perturbation to a data instance, how big of a change we see in explanations. And what we have plotted here is the percentage increase in stability compared to Lime, at least the top plot. So what you see here is the baseline for different data sets. For all data sets, we definitely see increase in stability with respect to Lime, like our method has a better stability. And of course, this increase is more pronounced in some data sets like Compass or MNIST and ImageUnit, and maybe it's slightly less pronounced in German credit data, right? Okay, so we also did a user study just to we actually did this both with and without users, but I just wanted to talk about this in terms of a user study. But basically what we did here is we wanted to get a sense of our base Lime explanations like better than Lime explanations. So the intuition is that we take a bunch of users, we randomly assign them to base Lime or Lime. We only do this with Lime and base Lime, no SHAP here. And what we do is, let's say there is a user, we assigned him to base Lime. We mask the most important features selected by base Lime in an image, and then ask the user to identify the digit in the image. Okay. So the hypothesis here is that the more informative the features are, the more harder it should be for a user to recognize that digit once the important features are masked. And we actually made sure that the model itself is using the most important features using a variety of tests. So the model was very good. It was using the right features. It was well calibrated. We were just trying to see if users will have a harder time in figuring out what that digit is once we mask the most important features. So again, the intuition here is that the better the explanation, the more difficult it should be for users to get it right when the corresponding top features are masked. And what we see is that the error rate was 25.7% for Lime and 30.7% for base Lime. So higher error means people are having a harder time recognizing the digit if the top features given by the corresponding method are masked, right? So this shows that our explanations are more informative than Lime explanations, okay? So I'll just conclude this and maybe I can pause for quick questions. And if we have more time, I can get into the second piece. So just as a summary, I just want to mention that this is one of the initial solutions that is addressing the challenges associated with fidelity, stability, consistency in the definition that I just clarified, and scalability issues associated with very popular post-hoc explanation techniques like Lime and SHAP. And it's a novel Bayesian formulation for capturing the uncertainty associated with local explanations. And we also leverage the uncertainty estimates to compute the number of perturbations required to generate explanations in such a way that the resulting explanations satisfy user-specified levels of uncertainty. And we are also able to employ our Bayesian framework to generate explanations efficiently. And I think this is an important piece in ongoing research on explainability. We need to kind of continue thinking about assessing the goodness of and improving the reliability of explanations. So that's a critical piece going forward, and work is just getting started. Okay, so maybe I'll pause here and see if there are any more questions. If there is more time, I can also just mention briefly about the other direction.
I have a quick question.
Yeah.
How did you sample the Z's? From what distribution?
Oh, so the Z's are actually the same kind of perturbing process that we do in Lime. So which is essentially you take a point and then kind of perturb it using like as adding a Gaussian random noise or so, and then generate the Z's.
So, well, once you have that pi sub x,
Yeah.
Aren't you incentivized to sample Z's closer to 0?
So the Z's are sampled independently of pi sub x. That's
But if you think about the sample complexity in your theorem,
right.
Aren't you incentivized to actually sample Z's closer to 0?
Yeah, but we are not sampling Z's. That's the point I'm trying to make. So Z's are things that are already, think of it as like somebody has given us Z's.
I understand, but like I'm trying to reframe the question a little bit.
Okay.
Like I assume pi is something like a radio basis function around x.
It's almost like an L2 distance. That's
Yeah,
that's
so,
the
so it's like an
pi.
L2 distance or radio basis function around x.
Yeah.
So you get what it's basically saying is that the data points closer to x are more informative, right? Or it gives higher weight.
That is correct. Yeah.
So if I want to, if I were to believe that completely, then and I want to get as reliable of an estimate as possible with as few z's as possible,
Mm-hmm.
wouldn't I want to sample z's very close to zero?
So there is also a bit of a trade-off, right? Because at the end of the day, you're also trying to like fit this linear model, or like get your feature importance vector. So for that, you also need to have like some distinction between the two classes.
Sure. I'm just commenting on what I think is, if you were to believe this theorem completely as the
Yeah.
whole story,
Yeah.
would be the logical conclusion I would draw.
Yeah, the point is to still sample points around X. I guess the local neighborhood around X is what we are focusing on. So yeah, ideally we should sample points closer to X. So I think that is in sync with how we are thinking, because it's a local neighborhood, right? You want to get points or samples in the local neighborhood. So your intuition that we'll sample points closer to X is
Yeah,
correct.
but suppose I chose, and I'll let other people ask questions too. I suppose I chose a pi function
Yeah.
that like falls off very quickly, like a radio, like an RBF kernel.
Yeah.
Where with a very small length scale.
Right. Yeah.
Then like, any z I sample that's like too far away from x has no weight at all.
Mm-hmm.
Right? Like in the extreme case where the length scale is arbitrarily close to zero,
right,
of the RBF kernel for pi,
right,
then the only z's that matter are the ones that are arbitrarily close to x.
right.
So,
So
anyway,
you-
it's just I mean,
yeah, no, I think that's right, but I'm just trying to understand. So is your worry that, oh, we might just end up sampling X repeatedly?
I'm wondering if there's like a more to the story. That's all.
I mean,
Right.
I think that there's something wrong with that, because if you just sample X repeatedly, your covariance matrix of your data is going to be singular.
Yeah, I
There must
agree.
be some term here that's
I'm just trying to like follow the implications of this theorem to its completion.
Well, I'm guessing, I mean, I don't know the theorem.
Yeah.
I'm guessing there's
So-
some term that'll.
Okay. All right. That's fine.
Yeah.
I was just a little puzzled. That's all. Yeah.
Right. Yeah, I guess, I mean, just kind of at a high level, the implication of the theorem is basically that I guess this G is the required number of perturbations, and then we are sort of plugging in some parameters there, where some of these are like user provided inputs essentially, and we are trying to estimate what is the required number of perturbations. Yeah.
Right. Yeah, I mean, it is a little strange. I feel like there must be something in this theorem that's countering that effect. But I did have another quick question. I guess I don't know if there's time, but I was wondering, so you've been kind of talking about uncertainty. It's a bit of a more high level question. You've been talking about uncertainty for improving Lyman SHAP, but the uncertainty doesn't actually show up in the end when you show the user the explanation. But it seems like knowing that the explanation is uncertain is intrinsically really useful as a user, because I want to know if there's uncertainty in the explanation. Is this something you've thought about or explored at all?
Yeah, you mean in terms of the user study, like showing people the uncertainty
Not
estimates?
This specific user study, but I just mean more broadly, like
More
is
broadly,
this
yeah.
something that's-
So recently we have also been, I guess, post submission, we have also been thinking about few other things, which is essentially like articulating or trying to quantify the benefits of having the uncertainty piece in the explanations, like how would users perceive that? So yeah, we are trying to run some experiments with that to just see like how it is influencing people's trust, and like how they're able to like trust an explanation less or more depending on its uncertainty. So that's like a bit of an ongoing process. So I think it's been, I think that's kind of a piece on its own. So how people are like using uncertainty to think about all of these other pieces, and how much they trust explanations based on uncertainty. So that's some ongoing work. Yeah.
Hello, is there time for one more question?
Yeah, sure.
Hi, this is Shupir here. Great talk. I had a quick question on. So it seems that is it true to say that what you have done here is quantify the uncertainty in the explanation mechanism? Have you looked at how the uncertainty in the model itself kind of percolates down all the way to the explanations?
Yeah, no, that's it's a very good point. So this work, of course, does like very little to kind of capture that or contribute to that. We have been thinking a bit more about that after this work. So we have been trying to understand how the uncertainty associated with a particular prediction or a set of local predictions of a model, how does that translate into explanations itself? Is there any correlation at all, or is it like purely a more a function of like I guess the explanation method? So those are questions that we have been asking, but of course this work is not touching upon that at all.
Great, thank you.
Right. Okay. So if there are few more minutes, maybe I'll just mention the other piece in passing. Of course, I'll not have time to cover everything, given that it's 4:53 by now. So I will just mention this work in passing. So this is a work from ICML 2020. It's about robust and stable black box explanations. This joint work with another student, Nino and Oscar Pastani. The idea here is that we were thinking more about global explanations, so where the goal is to explain the complete behavior of a given black box model, right? So that's a global explanation. The goal here is to basically that the global explanation will provide a bird's eye view of the model behavior. And why do we need these? They can help us detect big picture model biases persistent across larger subgroups of the population, since it's impractical to like manually inspect each and every local explanation corresponding to every instance to ascertain big picture biases. Some kinds of like a summary or like a global capture of what the model might be doing can be extremely helpful in detecting big picture biases. And one can think of global explanations as being complementary to the local explanations that we talked about earlier, right? And there have been several popular approaches for explaining the global behavior of the model. The idea of these approaches is essentially like we take a predictive model, we have some input data, we'll pass these input data points through the model, and then we get a bunch of predictions. Now we pass all this to an explainer algorithm, and that will in turn approximate this behavior of the complex model on the data that we have using simpler models. So that's like the model distillation technique. You are just trying to approximate a complex model using a simpler model, right? And several previous approaches or works tried to do this. For example, one paper tried to use decision trees to approximate the behavior of complex black box models. Some of our work tried to use decision sets and so on, right? The problem with these model distillation style global explanations is that they're highly data dependent. And why is that a problem? So for example, think of it as we have a distribution which is P of x1 comma x2, where x1 and x2 are perfectly correlated. And now we have a black box which essentially outputs this function, right? So it's the indicator variable of x1 greater than or equal to 0. So if x1 is greater than or equal to 0, it outputs a 1, otherwise it outputs a 0. Now we can have an explanation. So the global explanation picked by these distillation methods can actually look something like this, because x1 and x2 are perfectly correlated. So this explanation can say something like, oh, whenever the feature value x2 is greater than or equal to 0, then it's a 1, otherwise it's a 0. So that's the fit that could happen. And based on the fidelity based measures, this e hat, the explanation that we see above, will have perfect fidelity because it will match all the predictions of the underlying model on the data that we have, right? But it is still completely different from B star, right? But for this data set, it works because x1 and x2 are correlated. But if the distribution on x1 and x2 shifts, the explanation may no longer have high fidelity because now the correlation has broken and it's saying completely something completely different than what the model is saying, right? So basically, the point is that these model distillation based global explanations are not really robust to distribution shifts, and that's a big problem. So how to mitigate that was some of our work. Okay. Uh, so I will just quickly show a couple of summary slides. What we were trying to do is basically propose this like framework called as ROPE, which is robust post hoc explanations. And the goal here is to generate explanations that are robust to distribution shifts. And the framework that we had is like flexible. It can be instantiated for both linear model or rule-based explanations. And this was one of the initial approaches to think about robustness of explanations with respect to distribution shifts. And the high level objective is something like this, where we have a minimax objective that is probably typical of adversarial ML literature. But this is a typical standard supervised learning loss for learning explanations, where we are trying to minimize the expected loss between the explanations predictions and the black boxes predictions. But as opposed to just minimizing this expected loss, we were essentially minimizing the worst case loss over several possible distribution shifts, right? Modeled by a delta that we have. So we were essentially, in principle, we were considering each point X and then several shifted or perturbed versions of it, and then computing this loss on top of all those perturbations, right? So the worst case loss across those perturbations. Okay. So given that I'm almost running out of time, I can just show you one result here and move to the summary and conclusions. So in order to evaluate how successful this approach is or how effective this approach is, we considered a bunch of like data sets which had distribution shifts. For example, Bail or healthcare data set, where we had data from two different entities, like two hospitals or two codes. And we were trying to sort of generate the explanations using the first data set and trying to see how well they work with the second data set. So that is roughly the evaluation scheme. And what we saw was that these are a bunch of baseline methods. Again, we were working with global explanations throughout the evaluation. What we saw was that with some of the previously proposed methods, the drop between the train accuracy, the original data set's accuracy, and the shifted data set's accuracy was pretty huge. Whereas with our methods or the framework that we had, this drop was like much, much smaller compared to some of the baseline approaches. Okay. All right. So hopefully this talk kind of discussed a little bit about some of the critical problems in XAI literature at the current point. So we need to rigorously evaluate explanation methods. So that's, I think, a very critical problem. So there are some solutions, but this is not like a solved, addressed problem. So we need to constantly think about, are explanations output by these methods accurate? Can they mislead users at all, and so on? So we can't just blindly trust on the explanations provided by state-of-the-art approaches. And thinking about improving the reliability of explanation methods is also key. So that is, again, ongoing research, and the past two works that you have seen through this talk are just like first steps. There is a lot more to do there. And another piece that could be interesting going forward in the future, assuming we have rigorous frameworks to evaluate our explanations and also improve the reliability of explanation methods, the next step would be to think about explainability as a more of an interactive dialogue, as opposed to just like single shot explanations coming out and users trying to like make sense of them, right? So as opposed to that, if they're more interactive, it could be like a question answer kind of a dialogue, which could be more helpful. Okay. So with that, I think I would like to pause here and take any more questions. I guess we're on the dot. Thank you so much, everyone. Thanks a lot for your time.
Yeah. Thanks so much for the great talk. I think we have time for just maybe one or two more questions.
Yeah, I'll have one quick follow-up. So you, in the first half or the main part of the talk, you talked about this trade-off between consistency and scale.
Mhm.
And the main sort of angle on scale is you don't know how much is enough.
Yeah.
I guess part of what I was asking, it was, how do you make this, how do you make it more scalable, right? It's not just how much is enough, but how do you make what is enough a lower number?
Right. Yeah. So the answer to your question of how do you make what is enough a lower number lies in this uncertainty based sampling, where like earlier, if we think of line, you would randomly perturb and then use that to kind of generate neighborhood and so on, right? And whenever you generate a perturbation, you also need to query the black box model for label, because only then you can fit like your explanation model on top of it, right? So whereas as opposed to doing that, what we were doing with respect to also improving that scalability piece is, don't just take any random perturbation and go query the model. Of course, generate a perturbation, but only query the model for the labels of those perturbations on which your learning algorithm is most uncertain about. So you don't do random querying anymore. You basically compute the uncertainty of your learning algorithm, and then when it's uncertain, then you take that point and query the model, right? So that also helps us, like, bring this upper bound down of like what is exactly the required number of perturbations. So we can do it much faster than even the required number of perturbations that we are computing through that theorem. So it can even be lower in practice because of this uncertainty based sampling, right?
Okay. Yeah. So thanks again for the great talk, Hema. And yeah, thanks everyone for joining, and I'll see you all at the next NeuroSim webinar.
Thank you. Thanks so much, Oscar. Thanks everyone. Thanks. Bye.
Bye.